right, hello everybody. So we are heading into our last unit of the school year, which is crazy, on acids and bases. We're going to touch on a couple of brief topics. We're not going to go super duper in depth, but we will kind of get a broad sense of what acids and bases are. And so here we go. You've probably heard of me talk about acids and bases before. We've used hydrochloric acid and sodium hydroxide in the lab, and so you're somewhat familiar with them. So a couple of these slides will probably review things that you already know, and then the last couple of slides will introduce some new concepts to you. So today we're mainly focusing on concepts and definitions, and then we'll dive a little bit deeper next class. So your assignment for today is to listen to my screencast while studying the slideshow. And then when you've listened, you've looked over the slideshow and you feel confident, you can go ahead and complete the exit ticket, which is linked for you below. All right, so to start off with some characteristics, acids and bases are very different from each other, and they differ in a couple of really meaningful ways. First off, acids are sour. So acids, an example would be a lemon. You bite into a lemon and you pucker, it's sour. Whereas a base, something like a base, is usually more bitter. So soap is a base. Um, and then bases feel slippery. That's why soap is kind of slippery sometimes, whereas acids do not feel slippery. Acids, if you were to expose them to a metal like aluminum, magnesium, most of those metals will react with the acid to form hydrogen gas, whereas you do not get a reaction to produce hydrogen gas with a base. Acids will turn litmus paper, which is pH paper. We've worked with them before. They're those little strips of yellow paper. Acids will turn it pink, while bases will turn it blue. And then acids will corrode metal, while bases will not corrode a metal. So those are some of your basics, as well as the pH scale, which I assume is something that you've heard of before. I know we've talked about it. We did that lab, I think it was before Valentine's Day, where I gave you that piece of paper that had been soaked in the cabbage juice, and which is an indicator, and you took a bunch of different things of different pH levels and put them on it, change it different colors. So 1 all the way down here is an acid, all the way up to 14, which is the most basic, 7 being neutral, where pure water stands. All right, so some common examples of acids that you've heard me talk about before, we've used in the lab, include sulfuric acid. Sulfuric acid is actually the most produced chemical in the United States, which is pretty interesting. And that's because it's used widely. Production of paper, fertilizers, car batteries. Nitric acid now is extremely volatile and evaporates really quickly. It is, from experience, one of the most painful acids to get on your skin, and it is also used in the production of fertilizers as well as explosives. And then lastly, the one that you are most familiar with is hydrochloric acid. We use it all the time in the lab. It's used to purify magnesium that's found in seawater, and as you probably learned in biology class, it is part of the acid that is in your stomach. And we hear about bases much less often. We've worked with sodium hydroxide. You probably know about sodium hydroxide. It's most common used base. Industrial, it's sold as, it's called soda lye, or just lye. You've probably seen it in your bathroom, used to like clean the floor and the grout and stuff. And it's also used in drain cleaners and hand soaps, so a wide variety of uses. Magnesium hydroxide is used in milk of magnesia, which you can buy at CVS. It's for heartburn. And then lastly, potassium hydroxide, which is used in batteries. Hopefully what you've noticed as a general trend is my acids all have hydrogens, and my bases all have hydroxides. Now, the whole hydroxide thing isn't always going to be true, but for right now, let's just keep that in mind. All right, so generally speaking, An acid, so going back to what I just pointed out, an acid solution contains more hydrogen ions than hydroxide ions. So it's got more OH plus than OH minus, whereas a basic solution contains more hydroxide ions than hydrogen ions. And then a neutral solution is going to contain an even number of hydrogen and hydroxide ions. And there are a whole bunch of different models because there are a whole bunch of different chemists who studied acids and bases, and they all have their own definitions for what an acid and base is. There is Arrhenius, Bronsted, Lowry, and Lewis, all named for the scientists who came up with them. We're not going to worry about Lewis today because he's very outdated and he's also kind of complicated and talks about like electron transfer and stuff, which we are not going to get into. But we will chat about Arrhenius and Bronsted Lowry. This guy's also kind of outdated, so Bronsted Lowry is most definitely, without a doubt, the favored acid-base definition. All right, but first off, the Arrhenius model. So an Arrhenius acid is any substance that contributes an H plus ion to solution. Now, H plus ions we sometimes also refer to as protons, and I'm just going to say that right now. So sometimes you'll hear H plus referred to as a proton. That is because technically the H plus ion has lost an electron. Hydrogen has one proton and one electron. Since it's lost one electron, it's literally just made up of a proton, and that's why sometimes you'll see this referred to as just a proton. So an Arrhenius acid would contribute H plus ions to solution. So for example, hydrochloric acid, when it dissolves in water, it's going to unleash H plus and Cl minus, so that H plus is what's making it, oh, I didn't want to do that, is what's making this an acid. Arrhenius base is going to contribute a hydroxide ion to solution. Hydroxide is one of your polyatomic ions. So sodium hydroxide dissociating into Na plus and OH minus. Basic sodium hydroxides giving off an OH minus into water solution when it dissolves. Now, the reason that Arrhenius isn't so popular today is because what you'll notice in the Arrhenius definition is that it has to contribute this ion to solution. Not all acids are in solution, so that's one of the things that we don't love about Arrhenius, is that it's only considering acids basically when you add them to water, or bases when you add them to water. Also, not all acids are going to donate H plus and not all bases are going to donate OH minus all the time. So that's a crazy thing too. We're not going to talk about acids and bases that don't donate those, but it's not true of everything, and that's why Arrhenius is a little bit outdated. The favored model is the Bronsted-Lowry model. So a Bronsted-Lowry acid is any species that's capable of donating a proton. So instead of a hydrogen ion, we're referring to H plus now for Bronsted-Lowry as a proton. And we're not saying it has to be in solution. It's any species. Bronsted-Lowry base is any species that's capable of accepting a proton. So I said something wrong on slide 7. Acids basically almost always donate a hydrogen. Bases don't always donate a hydroxide. So let me clarify that. I was realizing that as I was looking this over. So bases don't necessarily need to donate hydroxide. Sometimes all they're doing is accepting a proton. So, big thing. Acids donate H+, bases accept H+. That's the definition you want to remember for acids and bases. There are some substances that can act as either acids or bases, and we call these substances amphiprotic. Water would be a classic example of a substance that can act as both an acid and a base. So down here, just to explain what this is an example of a Bronsted-Lowry acid-base pair. Here we have the sulfuric acid. So in this case, sulfuric acid is acting as an acid, as it will, and water, it has chosen to act as a base because it's with an acid. If water was with another base, water would be acting as the acid. Sulfuric acid, what it's going to do is it's going to give one of its hydrogens to water. So because sulfuric acid is giving up a hydrogen, it's the acid, and because water is accepting a hydrogen, it's the base. So this guy over here, the bisulfite ion, is sulfuric acid after it gave up a proton. And then this guy over here, we call this hydronium, H3O+, it's another polyatomic, is water after it gained and act as a base. So ignore conjugate acid, conjugate base right now. We're going to talk about that probably next class, but I couldn't get a picture without it, so you're seeing it a little early. And then, just last but not least, a couple more quick definitions. Mono, di, and triprotic acids. A monoprotic acid is an acid that contains only a single hydrogen atom, so it's only going to contribute one hydrogen atom in a chemical reaction. Example, hydrochloric acid, one hydrogen. Diprotic contains two hydrogen atoms. Example, sulfuric acid. And then triprotic, you guessed it, three hydrogens. This is phosphoric acid. All right, so that is all for today. Go ahead and complete that exit ticket. Email me if you have any questions, and enjoy your day.